Do you have any questions right now? Yes, sir. 529? Yeah. All right, all these are the same class of problems. They're basically something where you just have to understand how to apply Kirchhoff's current law and voltage law with complex quantities. That's it. And I want to make absolutely certain that you know how to use your calculator. I would encourage everybody to work this problem with me. So this is 529. Here, got a voltage of 120 cosine 5,000 T. And unfortunately, they would put everything in terms of L's and C's, so we have to calculate the P. We're going to do it fairly quickly. Here, they show you resistance of 60, and then they have an inductance of 16 millihenries. Then they have a capacitance here of 2.5 microfarads. And they have a resistance of 40 ohms. And then this is that value of Vs there. And they want I of T. And they want V of T right here. We're going to do this kind of quickly. They want V out of T. Now, the thing about this is, this more or less is a classic kind of a problem that your employer may ask you, and I say that very loosely speaking, because in this day and age, especially mechanical engineers, electrical mechanical systems, I suppose with aerospace too, and probably industrial, but I can't speak for sure on that. Everything right now is all being fused together. Go to a modern car manufacturer with any type of modern hybrid car. They have energy scavenging systems. How many know when they apply the brakes, they literally charge the battery? Do y'all know this? You're not going to get away from these things. They're everywhere. The electrical mechanical systems are everywhere. And you've got to kind of understand both. Now, if Aero, I don't really know that. I assume some of this stuff's going to be required. It's just a reality. So here they give you time domain quantities. But you'll notice cosine of 5,000 T, but it's been on forever. So essentially, we can go right to the phasor or frequency domain. Does everybody understand that? We're going to solve this problem in the phasor domain, and then we'll get the time domain quantities that they want. Does everybody follow the logic? First thing you need to do is find omega. By looking at this, what is omega, people? How many say it's 5,000? It is the coefficient of T inside that cosine argument. That's it. Now, if there was an angle in here, if it was plus 30 degrees, then we need to include that angle. Are you clear? It's not. I'm not going to ask this problem on this type of problem on the quiz today, but I'm going to tell you in the exam you will get this. So it's very important at least you understand the steps. So now I'm going to take this and I'm going to put it in the phasor domain. Everybody with me? We'll get all the quantities. So over here, we'll take it back to the time domain. I've got a voltage here, plus to minus. The magnitude is 120. The angle is 0 degrees, and the units are volts. We're in the phasor domain. Everybody with me on that? Next thing we're going to do is take that 60 ohms. It's 60 ohms every which way. So it's 60 ohms here. Now, instead of 16 millihenries, we have to put the equivalent phasor impedance. Everybody follow me on this. The complex impedance. And for an inductor, the impedance would be J omega L. That omega is 5,000. Do you all agree with that? If you do, raise your hand so I know who I'm talking to. Everybody must see this. It's critical. So I'm going to come down here and somebody's going to give me that value. It's J what? Can you just take 5,000 times 16 times 10 to the minus third? Or what? I'm sorry, is that micro or milli? Milli, right? Isn't it milli?
Milli.
All right, 10 to the minus third times 5,000, 10. So it's 5 times 16, isn't it, class?
80.
And what?
80.
Say again?
80.
80, yeah, so I can't hear sometimes. 80 ohms. Now over here on top, what is the capacitive reactance? It's minus J over omega C. Does everybody follow me on that? How many know that? You're going to need to know it for the exams. I promise you that. They're coming. And the more frequently you use it, the better off you are. So if you take minus J divided by omega C, what do you get? Anyone?
80.
80? Again? All right. And then you have to put 40 down here. Now, I'm going to make some points about this, and I want you to listen. They want this, I'm going to get the phasor current I right there, and they want this voltage right here. This is a very good problem that kind of showcases everything you need to think about. And this voltage, I'm just going to call it V out with a filter. Y'all with me? I want to make sure everybody sees this in the far back. Now watch. I have a voltage, right? Y'all see that? That voltage is directly across both of these elements. Does everybody see that? It doesn't matter what else is linked on here. It really makes no difference. That voltage is here, and only that voltage will drive this current. Does everybody see that? Show of hands if you see that. Good. That means this value of I in the phasor domain, well, is just going to be that voltage, 120, at 0 degrees, you don't even need it, and 60 plus J80, right? So what is the phasor value of I in terms of magnitude and angle? I'd like it magnitude and angle now. Get your calculators out, do it. Make sure you're not going to mess this up. I'm trying to expose any kind of problems. So you get rid of them now before the quiz. I have too many people coming in. And I'm not talking about non-E's, I'm talking about E's. But my calculator messed up. No, you messed up. You didn't know how to use your calculator.
1.2.
Say it again.
1.2 to the measure 53 degrees.
1.2 at an angle of minus 53 degrees. Anybody confirm? Anybody? Anybody not getting that? I'm trying to help you. If you're not getting that, we'll send help. You may not like it, but I'll do my best to help you. Y'all get this? Make sure you get it. All right? Now, I'm going to go right to the actual time domain next, so please be attentive. I have magnitude and angle in degrees, right? Now, I don't like doing it this way, but I'll show you. For the time domain, that I, and what do we call it? This I naught of t right here, I naught of t will be that magnitude, 1.2. Then you put the cosine of omega. Omega happens to be 5,000. And then you add the angle. Now, what did I say about that angle? I've been yakking about this for a long time. What should it be in? The units. Radians. But we're going to leave it alone just because the author of this text feels it's okay And it's not really, but it is today. All right, y'all with me on this class? Yes, sir.
How do you know if it's cosine or sine? I saw some.
Always cosine. Now this is an important thing. So how do you know if they put a phasor form 20 at an angle of 30 degrees? Just go with me there, all right? It always assumes that's 20 cosine of omega t plus the phase angle. That is a standard in engineering, in electrical engineering, and I assume for mechanical too. They use that as just a standard for phasor analysis. You with me, class? All right. By the way, sine and cosine are related by 90 degrees, but I really don't want to confuse the issue now. We can play with that later. All right, so we got that, right? Now how about this? I'm just asking you. You can do it so many different ways. I want this voltage in the phasor. How are you going to get it? So many ways. Anyone? Somebody said, what? Voltage division. Do you agree with that? Yeah, you don't have to. You can get the current through there and multiply it by 40, but it's essentially the same thing, isn't it? So let's get this voltage in phasor form. So the voltage here is 120. Now, calculate this with me. 120. Now what do? For voltage division, take the element you want the voltage across, which is 40. I'll get out of your way. And divide it by the sum of 40, right? Plus, or minus in this case, J80. Can you give that to me in terms of magnitude and angle, please? Magnitude, angle. Far back especially, pay attention to this. Anyone? What'd you get?
53.67.
Magnitude?
Yes.
53, I'll put it over here. 53.67, and at what angle?
63.4.
63.4 degrees. Anybody confirm that? Did anybody not get this? Are you with me on this? You guys get it? All right. Now, in the time domain, what does it become? Class? Magnitude 53, right? I'm putting this in the time domain form. This is the observable form. So it's going to be 53.67 cosine of what, class?
5,000.
Right, 5,000 t and plus 63.4 degrees. Now it should be in radians, but I'm not gonna call it. I hate that. If it was my radar class, if somebody did that, they'd lose points. But I'm not gonna do it here. Y'all with me, class? All right, that's how you do this problem. Both, and by the way, because on the quiz, I'm going to ask you for voltages and currents of all the elements. How many can get the voltage across this? 60 ohms. What are you going to do? Yeah, you could use voltage division, but do you need to? If we got this current, what are you going to do? Just multiply it by 60, right? Y'all follow me, class? All right, so I assume you'll be able to handle this class of problems without too much angst. And really, the only thing you have to do is relax, all right? And just stay focused. Don't get distracted. I hated the outcome of the game too, but I can't change that. You gotta move on. Yes?
When you did voltage division, you said you're supposed to,
Hey, shh, go ahead.
when you did voltage division, you said you're supposed to use the opposite resistance.
No, that's current division.
That's what-
Y'all hear that? And don't confuse this. Voltage division is where you have a voltage across two series elements. For that, you always take the element you want the voltage across over the sum of the two values of impedance and then multiply it by the actual total voltage. Current division is where you have two parallel impedances And if you want the current through 1, you would take the opposite impedance value over the sum and multiply it by the current entering both. Y'all with me? Please don't make mistakes on that. All right. Now, is there another question? I mean, that was a good, the thing about it is we went to the time, from the time to the actual phase or frequency domain, back to the time. The only thing I didn't cover yet, and I'm going to spend a little time on that later, not today, is power. The one thing different about power here, remember for DC it was what? I times V, or I squared R, or V squared over R. You all remember that? With AC power, we're going to be getting to that, not today, but I'm just giving you a hint. AC power is the average power that an element would absorb over one cycle. And a capacitor or an inductor will absorb 0 watts. They will store energy, and then the energy will get back into the circuit, but they never dissipate it. Only resistors dissipate energy. That comes later. How many knew that? All right, it's important. You'll see why that's important. Okay, I mentioned that. So we're going to do I'm going to mention this too. You remember how when we did nodal and mesh analysis, we found 2 equations with 2 unknowns that you use your calculators to solve. Do you all remember that? You will not be asked to do that with complex numbers. Now the reason I'm telling you that is because some of your calculators will have a harder time than others entering that data. And I've come to terms with the fact you are not electrical and computer engineers, and we don't expect you to have the same level of angst. So we're going to try to make things smooth and straightforward. So I'm not going to, you guys in MEs are going to get that crap. I'm almost positive in some of your higher level courses, you're going to have all sorts of 3x3s, 4x4s. They're going to have complex numbers. So you're not out of the woods, but I'm not going to be the guy doing that for you. They used to do that, but I talked to my department chair and he said, nah, they got enough headaches. All right. Now, basically, if you look at that chapter, we're kind of done with it, aren't we? That's it. We've done it. We're going to move on in a second. I don't think, no, he's not here yet. I did get some new markers, right? do one. Anybody have any other questions? I'm going to do one more problem. We're going to be done with this chapter, but I wanted to do one that probably, at least in my opinion, is a little more challenging. This is going to be problem 5.32. All right, for this one, what he wants is this current I naught. That's 6 amps at 0 degrees. And he used any tricks in your toolbox to do it. Now, there are a variety of ways to do it. You can do it so many different ways, it's almost not even funny if you take a look at that. What are some of the ways you can do it? If I want that, what could we do? I'm going to give you a few. Let's see which one you choose. It doesn't matter. You can do it every way. We could what? Ground this, correct? I think you know what I'm up to. No, right? Look at this now. You've got what? V1 here, and technically you got V2 here, don't you? How many see that? You all agree we could do it with nodal? We could all, I know we're not going to do it with nodal. We could. We're not going to. Now, without me going through all this, how many see we can, actually, what can we do to simplify real quick before we do anything else? Anyone? I think these two can add up, can't they? How about just 2 ohms? Y'all see what I'm talking about? So why not make life easier than it is? So that's just 2 ohms. Sure, we could do that, right? Now hear me. And we could do mesh analysis. We could put a current here, a current here, and a current here. Can you all see that? Just a show of hands if you understand, we could absolutely write 3 equations. We could do mesh analysis. You all with me on this, class? But we're not going to do that. And we can do a couple other things. We could do Thevenin-Norton transforms. I'm trying to show you the options you have. This is a current source in parallel with that, correct? We could take this and turn it into a voltage source in series with the resistor. How many know that? So I could say that would be 6 times 2 or 12 volts in series with 2 ohms. And now I'm literally right here. Y'all see that? And now take that cutout circuit and put it here, and you'll see what I'm up to, but I'm showing you all the options. This is 1 ohm. And then you have, now I'm going to ask a question here in a second. Can you all see how I simply took this part of the circuit and connected it to the series resistance and series voltage? Show of hands if you can see this. Now, this one is a little more attractive. If I want that current, how would you get it? Well, not quite, yes, you could do voltage division first, but then you'd have to divide it by 1 ohm. But before you got that, couldn't we simplify a little? You agree with that? Sure, make it 3 ohms. Alright? You agree with that? We could go one step further. We could go back to a current source in parallel with resistors. I have 12 volts in series with 3 ohms. Well, 12 by 3 is 4 amps. And then that would be in parallel with 3. You all see what I'm up to? In parallel with J1 and in parallel with 1. This is the current they want. Now, y'all follow me in this? You don't. What don't you see? I mean, do you follow me or not? How many do? I'm just showing you the options. You got so many options. I don't care how you do it. I'm going to show you how I do it in a second. This is pretty easy right here. Now, hear me. I want this current, right? Couldn't I get a parallel combination of these two as a single value? What is it? Just 3 in parallel with 1, right? J1. And then you would have a net impedance here. And if I wanted the net current there, it would be that net impedance over the sum of 1 plus that impedance times 4, right? How many see that? Sure, you could do that. What other thing could we do? Well, I'll tell you what. There's so many possibilities. If I look right here, I'll tell you what I'd do right off the bat. If I was going to do this, I'd use Thevenin. I don't even think twice about that. I would first locate, I want this current, right? So what is Thevenin's actual, I call it Thevenin's circuit analysis, but what's the first step in the process? First, you got to identify the load or the element you want the voltage or current through. You all see that's 1? Everybody. Then what do? Well, I'll label. I'll just put our load is 1 ohm. What's the next step? Erase it, right? Get rid of it. Do you remember that? How many do? You're going to need to know Thevenin. Thevenin is your godsend. It's the thing that will save you so many times. So remove it. Now I want this voltage, right? Just think of how many different ways we can get that voltage. What did I do before? The transform current in parallel with a resistance is voltage in the series with that same resistance. Do y'all remember that? Just watch this, you'll get it. So that's going to be 12 in series with 2. Do y'all agree with that? Everybody? Show of hands if you do. Can you see it in the far back, guys? All right. What may I do now? Remember, I want this. This would be the open circuit voltage or Thevenin voltage, right? Do you remember that? So what's my next step? How about these 3 guys? Combine them into, can you all see this or not? That's 3 ohms, isn't it? I mean, can you read what I've put here or not? Y'all follow me? Sure, it's 3 ohms. What's this voltage going to be? I'm going to see it. That's 12 volts. There's 3 ohms in series with J1, right? What's this voltage going to be, the open circuit voltage? It's going to be 12 times J1 over 3 plus J1. How many agree with that? Don't worry about the value. But how many see what I'm doing here? I'm trying to make it as simple as possible. This is trivial. But you have to be able to see these things. because this is the stuff you're gonna have to rely on later especially, because it gets more complicated. If you don't see this, you'll be totally lost. So that's the open circuit voltage now, right? What is the next thing we need for Thevenin equivalent? We just got so we got Thevenin equivalent voltage, right? What do we do next? It used to be called R Thevenin. Or we need to look back and find the impedance across the element we removed. Do y'all remember that class? So if you look back, what happens? Well, this gets shorter, doesn't it? Correct? And you have 3 in parallel with what? J1. How many see it there in parallel? From the actual points right here. If you look back this way, you actually see Zn is going to be 3 in parallel with J1. How many see that? It's important you can see this. If you can't see this, you need to really kind of spend some time making sure you can identify these things. So 3 in parallel with J1. In other words, and I'm not even going to bother with this, you have open circuit voltage that would go here. And that's the value. Then you're going to have Z Thevenin here, and that is the series or the actual Thevenin equivalent impedance instead of a resistance. And then you simply attach your load, which is 1 ohm. And what they wanted was the current here, right? So that current would just be VOC over Z Thevenin plus 1 ohm. And that's really it. Now, that is, in my opinion, a much quicker way to get to the result. Some of you don't like complex numbers. You will get used to them. They're not bad at all, but you do have to appreciate how to do these kind of problems. And Thevenin, in my opinion, Thevenin analysis for this stuff is probably the easiest and quickest way to get most answers, if you want a single answer. Now, if you want the voltage and current, it's several different points. It's a little different, but if you just want a voltage or a current through one element, Thevenin is the way to go.